Alan Turing and biology. So before that, let's think of a little thought experiment. Okay. So suppose you are walking on the road, you find a stone. You don't care, right? It doesn't interest you at all. And now suppose you are walking on the same road and you hit a watch. Supposing this watch. It's lying on the thing, so you pick it up and now you start wondering that this is quite a complex device, right? There are the second hands, minute hands, all these things. They are running synchronously, and once one of them completes the 60 revolutions, the other one makes 1 revolution, and all these things are going on. So it makes you wonder that the stone can be created by chance. You don't care about the stone, but this this watch, that must have a maker. So someone must be creating that watch. Okay. Now this is the original. This is called the argument from design. This is the original argument, and this was considered to be a scientific proof that God exists. How is that? Because we are all complex beings. We are as complex, I mean much more complex than a watch. And biological organisms and all these things are much more complex. So the fact that we walk about in this earth and we are here must mean that we cannot be created by chance. Someone must have made it. And that someone, that maker, the creator is the God. So this is the original, the argument that scientific proof that God exists. Why I talk about it, and why I talk about it in today about Alan Turing is that Turing's interest in biology. Why did Turing read biology? I mean, Turing had only one paper in biology, by the way. And that is a paper that has been most cited of all his works. In fact, his citations of that biology paper is greater than all his works taken together. So that's very remarkable. I mean, most of us don't even know that he worked in biology and he had a paper. So his interest in biology was came from this two things. First of all, that he wanted to refute, he wanted to defeat this design from argument. Okay, I mean argument from design. Sorry. And the second that Professor Viswas touched upon is from his mother's biography. His mother said that Turing was always, from his childhood, he had this love of flowers. So he used to stare at the flowers. He used to go to the playground, and instead of playing, he would look at the flower and how the patterns are arrived and all these things. So then he took it upon himself to unearth how these patterns in flowers came into being. So flowers are quite complex. You see, there are 5 petals and so on and so forth. It's not a homogeneous thing, and so how did flowers come into being? So he wanted to explain biology. And the way, so his paper is called The Chemical Basis of Morphogenesis, by the way. So that's considered to be one of the earliest works of theoretical biology, biological modeling. Okay. There is very little connection to actual biology in that paper, and there is no proof whatsoever that this is connected to some biology. This is just some conjectures in this paper that, oh, the flowers may arrive because of this, the multiple heads of this organism, Hydra, may arrive because of this, but there is no connection to biology at all. So he just sets about doing biology in his own way, and his own way is through his mathematics and through his thinking. So his was the first paper, but before that there have been at least 2 or more papers on modeling in biology. But if you read his paper, he doesn't talk about them, he doesn't cite them, probably he doesn't know about them. And that's also typical of Turing. I mean, if he wants to do something, he would not go about and do a literature survey first. He thinks of a problem, he tries to solve it, that's all. And he publishes. It doesn't matter if there are some other works and other things. So coming back to biology, what is the paper talks about? The paper tries to talk about, so the original argument from design has been defeated by Darwin, right? This whole original species thing. And Darwin showed, and Darwin kind of proved that how biological organisms evolve and how they are originated and so on and so forth. But still, it asks that question that, okay, I know the fingers are like this, and this helps me in grabbing or hitting or something, doing something, okay? But this shape, this is just a function of the shape, correct? That my fingers, if my fingers are like this, I can do certain things. So that's why they survive. But how did these fingers came into being? What is the origin? What is the morphogenesis of these fingers? That is not answered by Darwin's biology, and that is still a very open question in biology, okay? And Turing wanted to this, so his paper tries to solve this question by just taking physics and chemistry as the starting point. So he tries to solve biology, he tries to explain biology by just using physical laws and chemical reactions. So that is why this paper is called the chemical basis of morphogenesis. So what he tries of doing these things, are very gist of this technical piece is that there is a homogeneous thing when you start off as a zygote or in whatever one cell organism, it's homogeneous. And now there are different pressures, there are different chemical pressures and mechanical pressures that are acting on that homogeneous body. And he uses this diffusion, the idea of diffusion as we all understand, and he explains how this diffusion and rate of chemical reactions can lead to different patterns. And these are not random patterns, these are actually dependent on what is the amount of chemical that is there, what is the pressure that is there, and how these things hold on. Now again, go back and think of this, what I have just said. So I am starting up with a homogeneous thing, and I am ending up with different kinds of shapes. These shapes are not homogeneous, by the way, of course not, right? But this finger is much taller than this position here, and so on and so forth. So I start off with something homogeneous. I am using diffusion as one of the building blocks, and I am getting something non-homogeneous or heterogeneous. This is opposite to what we know about diffusion. What is diffusion? Is that there are two kinds of things. From the higher concentration, things diffuse, and eventually they become of the same concentration. So diffusion actually makes things homogeneous. But he is using diffusion to show how homogeneous things are getting into non-homogeneous things. And the catch here is that there must be at least two substances, chemical substances, which he called morphogens. It's just the name that he made up, there is nothing like morphogens. There must be at least two of these, and their diffusion rates should differ, their initial concentrations should also matter, and the rate of chemical reactions. And because these are biological organisms, there are cells that are, or there are biological boundary cell walls that are hindering this diffusion and so on and so forth. So that's why, because of all those reasons, the diffusion can lead to something non-homogeneous. Okay, so that's more or less. I mean, now he models all these things as some concentration of these things, and then he shows how some linear equations can be used from those concentrations, because he assumes that okay, first you start off with an equilibrium and you perturb the equilibrium slightly, and if there is this perturbation, by the way, is very necessary. If you cannot perturb the equilibrium, then you cannot get any non-homogeneous shape. So there is an equilibrium which is assumed to be homogeneous at time t equal to 0. Then you perturb it slightly due to some noise or Brownian motion or whatever. That leads to this non-homogeneous things, and those equations and all these things are linear. So he to be tractable, for the mathematics to be tractable, he showed how to solve those linear equations and all those. Okay. Which is all fine, but so this paper came out in 1952, and he died in 1954. As a follow-up to this paper, he kind of collaborated with another biologist to actually show the effects in biology, the actual biological organisms or actual biological processes and all these things. Unfortunately, he died before he could complete the paper. So there is no biological proof as of then, and it took all of so what is the proof? So this is just a theory that he proposed, and this is just a mathematical biology theory. And what is the status of his proof is that in 1990 probably, it was first showed that using his equations and using his model, you can create certain chemical patterns in some inorganic compounds and all these things. Okay. But this is only in 2012, February, that people have actually found out that these are actually present in biological organisms. So there are certain ring patterns in the roof of the mouth of mice. So then these researchers have found that you can explain the ring patterns using just two genes, which is essentially equivalent to the morphogens there. That these two genes are called FGF and SHH, if you are interested. And you can explain the ring patterns and the differences in the ring patterns in the different mice cells and different things, just using his equations. So that's a very telling proof of that his theory ultimately may work. Okay, or at least it works in something. Of course, there are lots of assumptions and all those things, linear assumptions because the concentrations are low and all these things. There are lots of things, but at least this is a direction in which he is going to be, his theory is going to be proved. But going back to 1952, okay, so once he published the paper, Turing being Turing, he expected a huge, applause or recognition from the community, especially from the biology community. But what I told you is that the biologists, only Darwin just came around, I mean Darwin's theory just came around, and biologists did not believe in mathematical biology at all. There was no theoretical biology. You are talking of some linear equations and showing that's how flowers are thing, without actually talking of a particular flower. That's just folklore. I mean that's just okay. Just because you're Turing, you are writing that paper. That was the thing. So he did not get any recognition, almost no recognition from the biologists at his time. So he was disappointed, and that is one of the reasons why it took him time to complete that other paper, which he could not complete in his lifetime. So he was disappointed. He actually wanted more, adulation or these things from the biology. He thought he defeated this argument from design very much, and he thought that okay, this is the end of. This is how at least you can explain how biological patterns form. Of course, he did not get that, so he was disappointed. But that is little, that he expected a little too much. Looking at the historical context and how things used to be. His work certainly was not neglected by the biologists. It was not that biologists trashed his work. In fact, as I told you, this is the most cited work, more cited than any of his other works, taken together. So his work was looked upon, his work was worked upon by other biologists, but he probably, I don't know, what he said in the other commentaries about his paper and his life is that he probably expected too much. Apparently he broke into fights with biologists about this. Okay. But yeah, whatever, that is all Turing, and so his contribution to biology is only this one paper. And there is a saying that one of the biologists actually told him, or even must be a folklore, that one paper does not make you a biologist, no matter how successful that paper is. So yeah, he did not take it very nicely, Turing. But anyway, that's all. These things now you read. There is no one to say whether this happened or not. This is what you can kind of project upon him. But that's all. That's all that I was wanting to tell about his contribution to biology. So his was the first, almost one of the pioneer works on theoretical biology, on biological modeling and modeling of how patterns emerge in biology. And he explained it using only chemical reactions and physical processes. And it is kind of strange if you think of it, that he being he being the inventor of this Turing machine and these ideas of all these things, he completely neglected genes. And in his paper, he talks of genes as just catalysts in reactions, and then he says we can now ignore genes. So this is after Darwin, by the way. Do imagine what he is trying to do. He is trying to neglect the most important piece in this biological jugglery at this time. And he's saying that it doesn't matter. Genes are there, genes will be there. The concentration of genes doesn't matter because the concentration of genes doesn't change. Genes are just catalysts. They just increase the rate of chemical reactions. And what we need for this modeling or what we need for this biological formation is just the rate. I don't care how that rate is influenced. I just need to know the rate, and that's all. And from there on, I can solve the biology. Okay. So he ignores these genes. Of course, he ignores this genetic programming. This AI kind of things. So in a way, he is like a new man. He is ignoring himself. He is ignoring his own work. He is ignoring his own experience in other fields of computer science, AI, and all these things. He just trashes all of those. He starts off saying that this is a physical-chemical reaction, and that's all. So this is kind of strange as to why he did it. And there is. I have been reading about it. I don't think there is a satisfactory answer to why he did that. And so only plausible thing is that he believed in that. He believed in his model so much that he kind of ignored other what you say, other signals to that. There may be more things to this biological formation than just this physicochemical reaction. So he set about doing that things in his own way, and he wrote this paper, and that paper is his most cited work in biology. Unfortunately, none of us knows it. And only that day, Satyadev was telling a nice story that the biologists, there are some biologists who know Turing as a biologist, and they don't know that Turing is a computer scientist. So, well, yeah, in some sense, he is justified later after his death that okay, biologists do take him as a biologists do claim him as their own and not computer scientists. So that's all. But at his lifetime, when this paper was published, he did not get. So yeah, that's all. So if you have any questions on this, or if you want to read this paper, so more than the paper, there are very nice commentaries on the paper, which are easier to read, because if you don't, I'm assuming you don't want to work out those differential equations yourself and try to apply them. If you just want to know more about his work in biology and his contribution and how later works build upon his work, then those commentaries are easier to read and understand.
So, under one comment, sure. It is in a way consistent with his character.
Yes,
because he's saying,
yes,
he's saying that I will ignore everything. Right. What is the minimum thing I need to do this?
Right.
I want to explain this phenomenon. I don't care whether it is real, unreal, it is there or not. This is all, reduce this.
Right. So it is very much in sync with his character.
Yeah.
This, as you were saying, his audacity, that saying that, oh, I don't even care about my own work. That's past. I start off from 0, t equal to 0, my modeling starts. I start off from ground 0. This is the full theory of biology. Yeah, that is true. You see, and that is why he was so much, frustrated by the reaction of biologists to his work.
So the idea is that the watchmaker, returning to the watchmaker, it will arise as a process of this asymmetry.
Okay, so there is a nice thing about, so even Darwin comments on this, is saying that, so Darwin's theory, if you go back to the origin of species, is saying that these mutations are random. Okay, that's just one way, and Darwin says himself that the mutations need not be random. If the mutations are random, then you can explain the whole evolution, that's true. But it does not mean that the mutations have to be random. The mutations can be caused by certain factors. So what Darwin was trying to say is that this argument that a watch cannot come out randomly, Darwin refuted that, saying that if you allow enough time and enough material and enough this thing, a watch will come out. Essentially, that's the, if you distill the argument. If you distill the argument. But Darwin himself commented in his book and later that the mutations, which is the basis of formation of new species, need not be random. And that is what Alan Turing worked on. He is showing that these pattern formations are not random. These are functions of the chemical, the concentration and the pressure and the diffusion, all these things. So that's all. So they are in sync, but that's refuting the original argument from design that God exists. I wish Piyush was here. Okay, thank you all.